Hey everyone, and welcome to This Explainer. Today we're going to unlock the secrets behind some of the most reliable problem solvers in our entire mathematical universe, rational numbers. All right, consider this puzzle for a second. 5x plus 7 equals 0. Do you think you can solve this using only integers? Well, if you subtract 7, you get 5x equals negative 7. But you literally can't multiply 5 by any whole number to get negative 7. Our basic integer number system just totally hits a brick wall here. And we need a much broader set of numbers to come in and fix it.
So, here's our roadmap for today. We're going to cover 1. The birth of rational numbers. 2. Defining the rational number. 3. Superpowers, or the math properties. 4. Inverses and identities. 5. Plotting on a number line. And finally, 6. The infinite numbers between.
Let's kick things off with Section 1, the birth of rational numbers. Math is basically just a historical record of humans solving harder and harder puzzles. Every time an equation gets stuck, boom, we literally have to invent a brand new category of numbers. To solve x plus 5 equals 5, we used whole numbers to get 0. Simple, right? Step up the difficulty to x plus 18 equals 5, and suddenly we need negative numbers, or integers, to reach negative 13. But then, we hit 2x equals 3. And integers just completely fail us. We had to break the mold and introduce a totally new system, rational numbers.
Which brings us to Section 2, defining the rational number. So what actually is a rational number? Well, it's any number that can be expressed as p over q, where both p and q are integers. In plain English, it's basically a fraction. But there is one absolute golden rule here. The denominator, that bottom number, q, can never, ever be 0. Because, as you might know, division by 0 is mathematically undefined. So as long as q is anything but 0, you've got yourself a rational number.
Moving right along to Section 3, superpowers, the math properties.
Now, these rational numbers aren't just floating around randomly. They follow very specific rules of engagement. And it's super fascinating to see how different operations behave. Take addition, for example. It has the commutative property, which just means the order doesn't matter at all. 5 over 2 plus 7 over 6 gives you the exact same result backwards. But subtraction? Absolutely not commutative. Swapping the numbers completely breaks the equation. A minus B is literally never the same as B minus A.
We've also got associativity. That's just a fancy way of saying you can change how numbers are grouped in parentheses without changing your final result. And then there's distributivity, which is basically spreading multiplication out evenly across a sum. So multiplying A by the sum of B plus C is exactly the same as multiplying A by B and then adding it to A times C. It's like a neat little mathematical package deal.
Okay, Section 4, inverses and identities.
I like to think of identities as mathematical mirrors. If you want a rational number to keep its exact identity, its additive identity is simply 0. You just add 0 and the number stays perfectly itself. It's the exact same idea with multiplication. The multiplicative identity is 1. Multiply any rational number by 1 and it remains completely 100% unchanged.
But what if you want to hit the reset button and perfectly cancel a number out? Well, that's when you use its inverse. For addition, the additive inverse just means flipping the sign of the number so they add up to 0. Like the inverse of positive 1/2 is negative 1/2. Simple. Now for the multiplicative inverse, you take the fraction and completely flip it upside down. The inverse of 4 over 3 becomes 3 over 4. Multiply those two together, and they perfectly cancel out, leaving you with exactly 1.
Let's see this in action. Section 5, plotting on a number line.
So, how do we actually plot a positive rational number like 7 over 4? It's really straightforward. We just look at the denominator. Since it's 4, we simply divide the empty spaces between our whole numbers into 4 equal parts. Then, starting right at 0, we just count 7 of those tiny spaces to the right, and boom, we easily locate exactly where our positive fraction lives on the line. And you know what? It works precisely the same way in the other direction. To plot a negative rational number, let's say negative 5 over 6, we just divide the space between 0 and negative 1 into 6 equal parts. Count 5 steps to the left, and that reveals exactly where our negative fraction lives. It's literally a perfect mirror image of the logic we just used.
And finally, my absolute favorite part. Section 6, the infinite numbers between. Okay, so here is one of the absolute greatest mind-bending secrets of fractions. What actually hides between them? What if we wanted to find the numbers between 1/2 and 2/3?
I mean, they look like they're right next to each other, right? Well, just follow 3 simple steps. Step 1. Find the lowest common multiple of the denominators, which here is 6. Step 2. Multiply the fractions so they share that new denominator. That gives us 3 over 6 and 4 over 6. Now, since there are obviously no whole numbers between 3 and 4, we move to step 3. We expand the gap. By multiplying the top and bottom by 10, we transform them into 30 over 60 and 40 over 60. And just like that, an empty, seemingly invisible space between 2 simple fractions opens up into a massive universe of brand new numbers. The rational numbers hiding between 1/2 and 2/3 now include 31 over 60, 32 over 60, 33 over 60, literally all the way up to 39 over 60. And honestly, the craziest part? If we had multiplied by 100 over 100 instead of 10, we'd find 99 whole numbers between them. We can literally do this forever.
So, I'm going to leave you with this incredible realization to take away from this explainer today. Unlike whole numbers, which are super rigid and limited, the rational numbers hidden between any 2 points are truly limitless. Think about that for a second. If there is an infinite, never-ending ocean of rational numbers perfectly tucked away between just the numbers 1 and 2, how incredibly vast is the math we haven't even explored yet? Thank you so much for exploring the limitless bounds of rational numbers with me today. Keep asking questions and keep exploring.